Hello YouTubers, fellow hams, RV enthusiasts, whoever else might be watching. Today I wanted to talk a little bit about what I've learned about solar with the setup in my RV. So we're going to talk about batteries first off and the wiring of a battery bank. There is a common rule for wiring up battery banks that a lot of people have mentioned. I haven't seen it explained. It's probably out there, but I thought I would give you my take on it. So we'll talk about that. And then we'll talk about the solar panels and the charge controller and the capacity and what I've done differently here recently after what I've learned from the few weeks that I've been using the system. So let's get into it. So first off, let's talk about battery banks. And in this example, we're going to assume that you've got 3 or more batteries. Although this would work for 2 batteries, 4, 5, however many. This is the way that you might think to hook things up. Paralleling all of your batteries, right here with these wires, these jumpers, and then hooking up your load or your charge source or both at one end of the bank. This is what they tell you not to do. And they tell you not to do this because it's going to it's not going to balance the batteries, and your batteries are going to age differently. This first one in the chain here is going to age faster than the next one, and that's going to age faster than the last one. But nobody really tells you why. The way that you're supposed to wire these banks up, by the way, is like this, where you are still paralleling the batteries, but your load or charge hooks up to this end here and this end down here. And this bit of magic will then balance your batteries and cause them to age together, at the same rate, so that their capacity won't become different between the batteries. But why? Why does this work this way? Well, let's go back to the bad example, and let's think about how we're hooked up. Okay, so your load or your charge source is coming in here on the end. Okay, and then you've got these jumper wires here and here and here and here that are between the batteries. Now, assuming that these jumpers are all the same length, okay. Length in this example doesn't really matter, but let's just assume that they're all the same length. And we'll call that length 1 unit, 1U, okay? So, get out of that mode. There we go. All right, so each of these jumpers is 1 unit of length. Now, wire has resistance, okay? Every bit of wire, no matter how long or how fat, is going to have some resistance. And when you have resistance and you have current flowing through the wire, you have what's called voltage drop. That's Ohm's law. That's basic Ohm's law. So let's say that, for example, one of these jumper wires has 5/100ths of an ohm of resistance, right? A really, really small amount, 5/100ths of an ohm. Let me pull out a calculator here. Okay, so we've got 0.05 ohms of resistance. And let's say that we're drawing 30 amps of current through that wire. All right, you've got an inverter, you've got a TV set running, you're doing something else in the kitchen, and maybe your kid's watching their TV in the cab over or something. You've got some current draw going on. Let's just say that we're drawing 30 amps through that wire. In Ohm's law, voltage is equal to current times resistance. So if we have 0.05 ohms of resistance, 5/100ths of an ohm, not much, but we multiply that by 30 amps, we get a voltage drop of 1.5 volts. So at 30 amps of current across this wire, the voltage that you see at this battery here and this battery here is going to have 1.5 volts of difference between them. So let's say we're charging, right? We're putting power into the batteries. And this battery has reached 14 volts. If we're still pushing 30 amps across that wire, that means that this battery here is going to be 1.5 volts lower. It's not going to be charged to the same level as this battery because of that resistance across that wire. And then by the time we get back to this battery here, we have 2 units of wire. So that would be 0.1 ohms of resistance. And if we take 0.1 times 30 amps, then we've got an additional a total of 3 volts of a drop. So if we're pushing 30 amps through this wire, by the time we get to this battery, we're 3 volts lower than we are here. So that's why this type of wiring is bad. These jumper wires are going to cause a little bit of voltage drop, and this battery is not going to be cycled as deeply and charged as much as this battery. And this one down here is not going to get cycled, is going to be cycled even shallower. It's not going to be drawn down nearly as much, and it's not going to be charged up nearly as much. So it's going to age slower than this battery, and this battery is going to age slower than this battery, and this one at the head of the line is going to need replacement far before these two. So that's why this is a bad way of wiring things. Why does this fix that problem? Why does wiring it diagonally across the bank like this fix that problem? Well, in this configuration, every battery in the bank has exactly the same amount of wire between it and the load or the charge source. All right, let's look at this battery first, okay? It has a direct connection on this terminal. But for let's say this is the negative side, we have 2 units of wire between the negative and the battery, right? So this battery is seeing 2 units of wire. Let's look at the middle battery. Okay, the middle battery has 1 unit of wire here and 1 unit of wire here. So again, this battery is seeing 2 units of wire between it and the load or the charge source. And finally, this one on the end, same deal. It's seeing 2 units of wire between this leg and a direct connection on this leg. So by wiring your battery pack diagonally like this, all 3 of the batteries in this case, and this works if there's 4 or 5 or however many batteries in the bank, all of the batteries have exactly the same amount of wire between them and the charging source and the load. So that's why you want to wire your battery banks diagonally. Makes sense, doesn't it? Okay. That's about that. That's enough about that. Now, what did I change in my system? Well, I had cheap batteries. What I bought for originally for when I was setting up the RV, I had to go cheap because I was really low on money. I'd put a lot of money into the mechanical systems, the brakes and such on the RV and the desk and other things, and I didn't have a lot of money left for the batteries. So I went with these cheap Rural King deep cycle, maintenance free, that's important, maintenance free batteries. Okay. They don't have a lot of capacity, honestly. They're automotive style batteries. They're designed to provide a huge amount of current over a short period of time. For example, when you're starting an engine, turning over the starter, that could be hundreds of amps. But they're not a big capacity battery, not a lot of amp hours. It's really, really hard to find out. The manufacturers don't rate the batteries in amp hours, probably because in this application, people aren't really concerned with it. In the application they're designed for. Marine battery, you're going to start your motor, maybe your under-scrolling motor a little bit, but they are deep cycle. Now let's talk about deep cycle for a second. For years, I assumed that a deep cycle battery was a bigger bucket, that it was going to provide more capacity so you could draw off of it for a longer period of time. No, that's not the case. Deep cycle means the battery can be drawn down below its safety margin more often without damaging it. In a normal lead-acid battery, you have plates, right? Parallel plates that are stacked up that go down into the battery, and then there's a gap at the bottom, below the plates and the bottom of the battery. And that gap is there for debris to accumulate. As the battery ages and bits of metal and stuff flake off the plates, they fall down, and that gap gives them some place to sit without shorting out the plates. Now, most lead-acid batteries have a safe range. You don't want to charge them much above 14 volts, and you don't want to discharge them far below 12 volts. I've heard 11.5 is the absolute bottom end, that if you discharge them below that, you start to damage the cells. What happens if you discharge them below that safe line is the cell plates start to deteriorate and more material starts to flake off of them and fall to the bottom of the battery. And if you deep cycle a standard lead acid cell, discharge it down below 11.5 volts, let's just say for sake of argument, 2 or 3 times, enough material will have fallen off those plates to build up at the bottom and touch the bottom of the plates and short out 1 or 2 of the cells. And then it's downhill from there. The battery is on its way out. You've damaged it. A deep cycle battery is designed with slight chemistry changes and a bigger gap at the bottom to allow for it to be abused and drawn below the safety margin multiple times without killing the battery. That's what deep cycle actually means. It doesn't mean they have more capacity. It just means they can be pulled down out of their safe zone multiple times without killing them. So that's what a deep cycle battery is. But now, as to capacity, okay. Up on top of the RV, I have 2 100-watt panels. So I have 200 watts. I've had people say, oh, that's not nearly enough. Well, in my case, it is. My usage is different from most people. Most people in an RV, they've got a battery bank, they've got an inverter, right? A big inverter, and they're running a television set, and they're running appliances and other things that are drawing a lot of power. They're using a lot of power. An inverter is not very efficient, so it's just going to eat power just running itself. But if you run a television set, that's a boatload of power, 4 or 5 amps. Easy, maybe more. So yeah, for most RVers, 200 watts of solar is not a lot. For me, I've adapted most things in here to run directly off the 12 volts, so I've gained a lot in efficiency. I don't have a television set. I don't watch broadcast TV. I haven't watched broadcast TV in like 12 years. I'll watch certain television programs that I am interested in, but usually through other means, using the laptop. So I don't draw a lot of power. In fact, in the over a month that I've been on the road, I've turned my inverter on once to use the vacuum cleaner. That's it. Everything else, run on the laptop. I don't use the inverter for that. I have a direct 12 volt to 19 volt converter. So I'm doing one step of conversion to bring power up for the laptop, and that's 42% more efficient than running the inverter and using the laptop's adapter. I showed that in an earlier video, so that's a big improvement there. The amateur radio gear all runs off 12 volts. I've adapted my audio amplifier for my speakers. It runs directly off 12 volts. I've adapted most things to run directly off the 12 volts for efficiency. So my power requirements are nowhere near what most people are. But still, with 2 of these Rural King deep cycle batteries, and they are, by the way, sealed, maintenance-free batteries. I can't stress that enough. They do not emit gas unless you abuse them. Okay, they're not going to be producing hydrogen and hydrogen sulfide, so it's not as critical to vent them, and you can put them inside the coach if you're not abusing them. If you're not rapidly discharging or rapidly charging them. If you were pumping 80, 90 amps of charge current in there, they might produce some gas, and they should be vented and in an external box or something. But in my case, I'm 25 amps is about the most I would draw from them. Maybe a bit more if I ran the inverter to run the vacuum cleaner or the saber saw or something. But they weren't going to outgas. Anyway, put that aside. I had to say that because I had a whole bunch of people comment early on in the build videos that I was going to kill myself putting the batteries inside here, and it's like, no, they're maintenance-free, sealed batteries. They don't outgas. Anyway, as to capacity, here's what I found in using the system when I was off-grid. If I used my radio in the evening when I didn't have any solar coming in, just off the battery, and I ran some power, 50 watts or so, maybe more, after an hour of just light use on the radio, I would have drawn the battery voltage down to about 12.4 volts. After another half an hour, I was down to 12.1 volts on the batteries. And this is with two of them, right? So an hour and a half of just playing on my radio, I've drawn them down to 12.1 volts. They're getting down to that level where it's like, okay, it's time to recharge them, you know? I actually pulled them down below 12 volts a couple of times, got down to 11.8. And that was just after a couple hours of just playing on the radio. So not a lot of capacity. They're designed to dump huge amps over a short period of time. They're like a pitcher. You know, you can take a pitcher of water and you can turn it over and dump all the water out in one go, right? It can deliver everything. Well, I didn't need a pitcher. I needed a big bucket, right? I didn't care how big the mouth was. I didn't care that it could dump a lot of current or not, because I'm not drawing a lot, but I needed the capacity. So drawing those batteries down to just below 12 volts one night, I thought this will be interesting to see the next morning how fast the solar panels can charge it back up. Right? Two batteries in parallel, down to 12 volts. The next day was a sunny day, and in about, it was under 2 hours, it was a little less than 2 hours, they were back up to 14 volts. And then my charge controller went into float charge mode. The way a solar charge controller works is it will dump the full current of your solar panels into a battery as it's charging it. Once the battery reaches a charged state, the charge controller will back off and just maintain a float voltage, usually about 13.7 volts. So it takes just enough energy from your solar panels to maintain that battery voltage. And any other energy that your panels are generating is just not being utilized. And that's how it was. I could draw those batteries way down to where they needed to be charged, and the next day, if it was a sunny day, within 2 hours they were charged up, and the rest of the day and the rest of the sun that I was capturing wasn't being utilized. It wasn't going anywhere. So I needed a bigger bucket. So what I did was I replaced 2 of these cheap deep cycle marine batteries with one of these, this VMAX charge tank. And this is actually a battery that is recommended by Renogy, who makes my solar panels, as one of their recommended storage systems. Okay, it's deep cycle, meaning that it's designed to be able to be pulled down out of its safety zone multiple times. But it is also an AGM, which is a glass particulate gel chemistry battery. So it's completely sealed. There are no vents at all. In fact, they say you can mount it in any orientation. You could mount it on its side or upside down if you wanted to, and it would still work. But it is 120 amp hour. Now, that's a lot of capacity, okay? If a battery was 100% efficient in a perfect world, 120 amp hour would mean it can deliver 120 amps for an hour before it's depleted, or 12 amps for 10 hours, right? However you want to look at that. That's what that rating means. In a perfect world with a 100% efficient battery, it could deliver 12 amps of current constantly for 10 hours. So that's a big tank. That's a lot of capacity. So anyway, bigger battery. It's 13 inches wide. I had to redo my frame that I mount the batteries with here under the desk to get that in there. But it's and it's heavier. It's 75 pounds for one battery. But it replaced 2 of those automotive style batteries. I actually had a net gain in less weight, which is good. I forget. I figured it out. It was somewhere around 50 or 60 pounds. that I'm lighter now by taking those 2 batteries out and replacing them with one of these. So how does it compare? I wanted to run it down. The first day I put it in, I got on the radio that night. I played radio for 2 hours, and I was only able to draw it down to 12.6 volts. It came down to 12.6, 12.7, and it kind of plateaued there, which is how I would expect these gel cells to work. You know, you're going to charge them up to 14 volts, they're going to settle to 13.7, and then when you start using power, they're going to come down slowly to about 12.6, and they're going to sort of level off, and they're going to sit there for quite a while and maybe drop a little bit, but they're going to sit there kind of at a plateau until they reach towards the end of their charge, and then they're going to start to fall off again. It's still dropping around the 12.6, but it drops a lot slower. So after 2 hours of playing radio, it was down to 12.6, and that's where it was sitting. And I kind of got tired that night, so I didn't draw it any further down. I don't know how much more I had, but definitely a lot more capacity than what I had with the other 2 batteries. The next day was a sunny, partly cloudy day, mostly sun. And it was about 2 in the afternoon before the charge controller went into float mode. So I was capturing a lot more of that energy that was being produced, whereas before it was being wasted. And I'll do another test where I'll actually draw this down to 12 volts, probably the next time I'm in the field. I'll really pull it down, and then I'll measure how quickly it charges the next day. But I suspect I'm going to be capturing more, storing more of that energy that my panels are producing instead of a little bit in the morning and then being full and just wasting the rest. So that's what I did to upgrade my battery. And the way I figure it, I have 2 100-watt panels. They can produce in direct sun about 10 amps to 11 amps, somewhere in between 10 and 11 amps of charge current. Let's say 10. If this battery was completely flat in a perfect world, 100% efficiency at 120 amp hours, it would take 12 hours of direct sun to fully charge the completely dead battery. So I think that that's a pretty good balance. It would take a little bit more than a full day of sun to fully charge the completely flat battery. So I definitely now have the storage capacity to capture that energy instead of wasting it. So that's what's going on there. Any questions, leave them in the comments. I know I babbled on a bit on this video, but I wanted to try to get as much information in there as possible. And I hope you found it useful. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.